Hello, we have here a uniform magnetic field directed out of the screen. There's a charged particle here, Q, moving rightward at this instant. So Q is going to experience a BQV force. For the direction, we use the Fleming's left-hand rule. Index finger pointing in the direction of the magnetic field out of the screen. Middle finger pointing rightward, because a positive charge moving rightward corresponds to a rightward conventional current. The thumb is pointing down. So Q is being pulled downward by the BQV force. Question for you. What will be the subsequent path of Q? Is it going to be parabolic or is it something else? Let me tell you why it cannot be parabolic. To be parabolic, the magnetic force must remain downward. But do you realize that as Q turns, the direction of the magnetic force must turn as well? See how your hand will move if you follow the motion of the Q. See? Your thumb must always remain perpendicular to your middle finger. So this is an important fact. The magnetic force always acts perpendicular to your velocity, and that's the signature for circular motion. So naturally, a charged particle will move along a circular path in a magnetic field, because naturally, the magnetic force acts perpendicular to your velocity. So the magnetic force always points towards the centripetal direction. If we ask you to calculate the radius of this circular path, you go back to Newton's second law, just that this time you are going to put in BQV to be the net force. The other side is the familiar centripetal force of mv squared over r. Rearrange and you get the expression R is mv over bq. So if you increase v, you do a circular motion but with a larger radius. Conversely, if you increase the magnetic field strength, Q will still do a circular motion, but you do it with a tighter radius. Now since we are here, let me point out something that's interesting. The time taken for Q to complete one revolution can be calculated like this. So T is 2 pi r divided by v. So it's just distance, which is the circumference, divided by your speed, which is v. Now replace r with this expression that we have just derived. Notice the v gets cancelled away. So the time taken to complete one revolution is independent of v. So if you travel at a lower speed, you do a smaller circumference. If you travel faster, you do a bigger circle. But the time taken is the same, whether you are doing this one or this one. I thought that's quite interesting. Okay, for the rest of the video, we'll just practice the Fleming's left-hand rule. So here we have a magnetic field directed into the screen, and you have a positive charge moving leftward. What's the resulting circular motion? Pause the video to buy yourself some time. If not, I'm going to review the answer now. Alright, Fleming's left-hand rule. Index finger pointing into the screen in the direction of magnetic field. Middle finger pointing leftward in the direction of conventional current, because positive charge moving leftward is conventional current leftward. Now the thumb is pointing downward, so that's the direction of the BQV force. We know it's going to do a circular motion, so this is the centripetal direction, which means the center of the circle is somewhere below. So the charge is going to do a circular motion like this, yeah, in an anti-clockwise manner. Get it? Okay, try the next one. Magnetic field coming out of the screen, negative charge moving upward. Pause the video to get yourself some time. If not, I'll review the answer now. Okay, Fleming's left-hand rule. This time, index finger pointing out of the screen in the direction of magnetic field. Middle finger pointing downward. Why? Because this is a negative charge. A negative charge moving upward is a conventional current that's downward. That's why the middle finger must point downward. So now your thumb is pointing leftward. So that's the direction of your BQV force, which means the center of the circle is somewhere here. So it's going to do a circular motion like this. Okay, next one. Magnetic field is leftward, positive charge moving downward. Are you ready for the answer? Okay, Fleming's left-hand rule. Index finger is leftward, middle finger is downward because conventional current is downward. Thumb is now pointing into the screen. That means the BQV force is directed into the screen. So into the screen is the centripetal direction. So the center of the circle is somewhere behind the screen. So the resulting circular path will be like this. So this thing is going into the screen and come back out of the screen here, and then into the screen and then come back out of the screen. And this position is when the charge is closest to us. If you are looking from right to left, then it's a circular path in an anti-clockwise direction. Okay, what about this one? Magnetic field is upward. You got a negative charge moving leftward. Pause the video if you have to. I'm going to review the answer now. So, index finger pointing up in the direction of magnetic field. The middle finger is pointing rightward, even though your charge is moving leftward because you are a negative charge. A negative charge moving leftward is conventional current that's rightward. Now the thumb is pointing out of the screen. So the BQV force is directed coming out of the screen, which means the centripetal direction is towards us. And the center of the circle is somewhere in front of the screen. So can you visualize the circular motion? It's going to be like that, yeah? Going to be like that. So it's going to come out of the screen here and goes back into the screen here and then come back out here and in again. And this position here is when the charge is furthest away from us. Or if you were to look from top towards bottom, then you see a circular path in the anti-clockwise direction. Okay, let's do one final one. So magnetic field is leftward, a positive charge moving rightward. So what is the circular path going to be? Do you see the circle already? Pause the video if you have to. I'm going to review the answer now. This charge is going to go straight. What? No circular path? Yep, no circular path because no BQV force. If you are moving parallel to the magnetic field, you will not experience any BQV force. Alright, that's all. Ta-ta!